perform a z-test for a statement about a mean and a statement about a proportion. In this video, I want to recap some of that stuff, and then I want to show you how you can do the last few steps on your own computer. Because last time I was just sort of gesturing at the chalkboard and saying we can calculate these tail areas, and I want to make that more definitive this time. So let's recap how we perform a z-test. A lot of it is exactly the same as a regular hypothesis test, but there are some key differences. So the first thing we need to do when we're performing a z-test is we need to clarify what the hypotheses are. If we don't know what we're trying to prove or what we're trying to assess, then there's no hope for us. So the first thing we have to do is identify an alternative hypothesis and a null hypothesis. The alternative hypothesis should be a statement of effect. It's usually phrased as an inequality. Sometimes, more often than not, we say that a mean or a proportion is greater than some fixed value, but sometimes we say it's merely different from some fixed value. And I would remind you that that's the difference between a one-sided and a two-sided hypothesis. The null hypothesis is a statement of no effect. It typically states that a mean or a proportion is equal to some fixed value, which we call the null value. After we clarify what our hypotheses are, then we need to collect some data. After we collect some data, we have a measurement of a mean or we have a measurement of a proportion, and we write x bar or p hat for that. You should understand the key difference between x bar and mu and between p hat and p. These are the statistics that we collect from the data. These are the parameters that describe the population. In order to continue here, I like to phrase this in terms of the null story, which is really an elaboration on the null hypothesis. The null story states that x bar or p hat should have been the null value predicted from the null hypothesis. If we really believe the null hypothesis, then we should really believe that it should have turned out to be whatever null value we have stated there in the null hypothesis. But we also accept that because this is a measurement and because it depends on random sampling, x bar and p should exhibit some natural variability. And we can calculate that variability. That's the standard error. So we can calculate the standard error by one of the two main formulas for standard error, one for the mean and one for the proportion. So if we understand that it should have been approximately the null value and that it's also going to exhibit some natural variability, then we should predict that it should be random, that it should be normally distributed with a certain mean given by the null value and a certain variability given by the standard error. But we also know, because we actually performed the experiment here in part 2, we know that x bar and p hat turned out to be some certain value. It turned out to be whatever it was. And that value is probably different from the null expectation. And so in the null story, we explain this as the consequence of simple dumb luck. We simply say, well, it was naturally going to be variable, and it varied that much. That's how much it varied. Then we have to measure in terms of what we anticipated that it would be, and in terms of how much variability we expected from it. How many standard errors away from the mean is it? And this is where we use that formula for the z-score. We take the measured value minus the null value, and then we divide by the standard error. Basically, that's a measurement of how far off our data is from the null expectation in units of standard error. So that gives us the z-score. The z-score is also called the test statistic, and that's a key piece of vocabulary that you'll be using on your homework. So finally, we have to ask the question, what are the chances of that? Our test statistic indicates that our measurement, x bar or p hat, turned out to be a certain number of standard deviations away from our expectation given by the null value. And we have to say, what are the chances of that? And that's the question of the p-value. But in order to answer that question, we need to refer to a normal distribution. And so I want to show you how you can do that yourselves using a computer. So there are lots of applets online that'll allow you to do this, and I've just kind of picked out one at random that seems to have a pretty good interface. So I'll link to this in the comments of the video. So this is an applet that allows you to plug in your z-score. Here it's referred to as x. It allows you to plug in the test statistic x into the normal distribution, and then it tells you how big the tail is. So let's plug in 1.6 here and see what happens. So this is a pretty nice graphical interface. It actually shows you a picture of the area. So why is this the key area? If our test statistic really was 1.6, that is, if our z-score that we calculated turned out to be 1.6, then that means that our data managed to fall 1.6 standard errors away from our null expectation of where it should fall. And then we have to ask ourselves, what are the chances of getting such a freak accident? Is that very rare or is that pretty common? And so what we're asking here is, what is the probability in a null distribution, in a normal distribution, of getting data 1.6 or more standard errors above the anticipated value? And so this whole area here, all of this area is going to be exactly equal to 1, which represents 100%, which represents 100% of all of the events that would happen in a normal distribution. These are the most common here because you can see these are the highest values on the curve. These are less common and these are less common. But all together they make the area makes up 100%, which is basically all of the possibilities for how these things can fall. The area of the tail represents the probability of getting 1.6 or more standard errors above the anticipated value, which is exactly what we're asking when we're asking for the p-value. So if we simply calculate this area, that is the probability of getting results like ours or more extreme. In other words, that's the probability of getting evidence as strong as we got or more so merely by chance. That's the question of the p-value, so that's exactly what we need. And here, this thing actually calculates this, not only displays the area for us so that we know what we're doing, but calculates the area exactly, and it's 0.548. If we were doing a standard hypothesis test with an alpha equal to 0.5, then we would be close but not quite here. The p-value would be almost low enough to get underneath this threshold of statistical significance. If our test statistic was 1.6, then we would almost be ready to reject the null hypothesis, but not quite. And this would actually be a non-definitive test. But if our test statistic is slightly higher, like 1.8, then that makes a small change to this area so that now this is only 0.3593, which is the same thing as 3.5%. Now, 3.5% is less than the threshold 5%. And so this would lead us to reject whatever null hypothesis and conclude that our alternative hypothesis is correct. So using this tool or any other tool like it, we can input the test statistic or z-score, and then we can get the tail area. And that tail area we will interpret as the p-value here. Now, sometimes you're not testing whether something is greater than a fixed value, but whether it's less than a fixed value. If this happens, then evidence in favor will typically be given as a negative test statistic. And in that case, you probably don't want the right tail here because you want to analyze when would the data be like yours or more extreme, but more extreme would be counting more in favor of your hypothesis that it would be less than a certain value. So instead of the right tail, you would probably want the left tail. So we can select a different mechanism here and we would get the left tail. So if the hypothesis stated that a value would be less than a given value, we would probably want a left tail here, and we would probably end up with a negative value for the test statistic. And no matter, we would get a p-value, and we would get 0.2275, which if the alpha value were 5%, would be sufficiently small to reject the null hypothesis in that case as well. Sometimes we don't want a left tail or a right tail. Sometimes we're doing a two-sided hypothesis test, in which case we would want to combine all the results that would give us evidence that strong. So if our hypothesis is phrased in a way that says, this machine is out of whack, it's producing parts that are different from the specified average, then the form of the alternative hypothesis will be a statement, the average is not equal to something. Now, if we get a test statistic of, let's say, 1.9, and we simply get a right tail test here, then we would say, look, this is recording all of the cases that we would accidentally get a test statistic of 1.9 or higher. But if we're really trying to measure whether something is just different from a value, then it could be different on the other side by just as much. And we would count that as equally strong evidence. And so anything better than 1.9 would count as equally strong evidence, but anything less than minus 0.9 would also count as equally strong evidence. And so for a two-sided hypothesis test, we're going to want to use two tails here. And so we select the other functionality here, and it combines two tails. So this is basically saying if we were off by 1.9 high, but we were also counting off by 1.9 low as equally significant, then we would combine those tails using this mechanism, and then we would get the total p-value, which would be the combination here, which would be actually a little bit more than 5%. Now, I recommend that you use this tool because it's what I'm using, at least in the short term. But the fact is, there are a lot of tools out there, and some of them have different functionalities. Some of them can't do the two-tailed test, as I just illustrated here. Some of them can only do the right-tailed test. And so you kind of have to adapt. Many of them, including the tables, can only do the left-tailed test. And that's kind of a pain, especially if what you really need is a two-tailed test. So sometimes you have to do a few geometric tricks. If you're working with a tool that can only do the left tail, then you're getting answers like 97%. Basically, this is telling you that this area here is 97% of the area. And you have to figure out for yourself what the actual right tail area would be. And how would you do that? You just take this number and subtract from 1. Or you take 97.1% and you subtract from 100%. So easy peasy, you just take this number and subtract from 1. The total area is 1. You subtract this left tail area from 1, and you end up with the right tail area. If what you actually need is the two tail area, then you might have to jump through some hoops. You might have to take this left tail area that the tool is giving you, and you might have to subtract it from 1 to get the right tail. And then, having the right tail, you might have to say, well, look, the left tail is just as big as the right tail, so I'll just take my right tail and double it, and then I'll have two tails. So sometimes you have to jump through a few hoops this way, but honestly, these are the only kind of little tricks that you have to remember to do. If you are working with a tool that can only do limited functions, and often it can only produce the left tail area. And then you just have to remember, sometimes if my test statistic is negative, the left tail is exactly what I'm interested in. But often, if my test statistic is positive, the left tail is the opposite of what I want, so I have to subtract from 1. And sometimes the left tail is, well, when I get the tail area, if what I actually want to do is perform a two-sided hypothesis test, then I probably want both tails because they both count as equally strong evidence. And then you just double this tail area. One way or another, whatever you compute here, once you get the tail area that you're interested in, that is the p-value. So if your test statistic is 1.7 and the right tail area is the right calculation, then your p-value will be 4.4%, which, using the standard threshold of significance of alpha, is statistically significant and will lead you to reject the null hypothesis. So this kind of tool is what you'll need to use in order to finally evaluate the p-value on the basis of the test statistic or same z-score, same thing. And then, of course, what do I do with the p-value? The same thing we always do with the p-value. If it's less than alpha, then we reject the null hypothesis. And we say the alternative hypothesis is proven to a statistically significant degree. But if the p-value is not less than alpha, then we simply say, I don't know, it's inconclusive. We may have preliminary evidence, but we don't have evidence one way or another. We don't have anything definitive in our test, and so our study is kind of inconclusive. So that's how we complete the entire z-test with the assistance of some sort of tool that's capable of calculating areas on a normal distribution.